Thank you, Ritabrata, and I guess welcome to everybody from me as well. So I'm very happy to announce our first speaker, Harcos Gergely from Budapest, who is going to tell us something about a new zero-free region for Rankin Selberg L functions. So the floor is yours, Gergely.
Okay, thank you, Julia, especially for the perfect pronunciation. So a big thanks for the organizers for putting together this event and for having me here. This is my third visit in India, and it has been spectacular so far. So I had a great trip, 18-hour trip on Saturday, and I just realized that out of the 16 biggest cities in India, I have now visited 5. So still counting. So this is joint work with Jesse Thorner. I will talk about a new zero-free region for Rankin-Selberg L functions. So this is a result we proved last time, but I thought it was okay to talk about this topic here. After all, it's not every day that you find a new zero-free region for L functions, and the paper is still under review. So, this zero-free region will be about GL1 twists of Rankin-Selberg L functions. So GL1 twists are very important in this talk. Let me introduce some notation and talk a little bit about GL1 twists in general. So FM be the set of unitary cuspidal representations of GL and A. So here in these slides, I work over the rational field, but everything I'm going to say works equally well over number fields. And then in particular, F1 is the group of unitary Hecke characters of the ideal class group. So that is unitary characters of the multiplicative group, so the group of ideals that are trivial on the embedded Q star. And it will be very important for us to have in mind that AQ star decomposes a direct product into the multiplicative group of positive real numbers and the norm one group of the norm one ideal group. So if you're not comfortable with ideals and such, don't be afraid. So here, what is important for us is special over Q. There's a very transparent description of F1. So every element of F1 corresponds bijectively to a pair of a real number and the primitive Dirichlet character, including the trivial Dirichlet character, and then the L function of that chi, to which this pair T psi corresponds to, is just Ls plus IT psi. So the first component of chi materializes as a shift of the L function, and then the norm one part, so the psi part of this chi materializes as usual in the parameter of the Dirichlet character underlying a Dirichlet L function. And for us, it will be super important that F1 is a group, and it acts on the set Fn via this familiar twist operation. So, very simply speaking, if you twist by such a chi an L function, you should think of as shifting the S variable by IT according to the T parameter, and twisting in the usual way by psi, the characters psi, the automorphic form, cuspidal representation or non-cuspidal automorphic representation underlying the L function. Now, very often, the set of unitary cuspidal representations, so unitary cuspidal representations are normalized in such a way that the central character is trivial on the embedded positive real numbers. So this more restricted family will be denoted by Fn star for us. So sometimes I will use this notation Fn star either for normalization purposes or just stating all the results and having a good understanding of them. So, so here is the normalization. So every element pi in Fn, so every unitary cuspidal orthomorphic representation of GLN can be twisted by a determinant character in such a way that the resulting pi star will lie in the Fn star family. So so for every pi there is a unique pair, T pi a real number, and the pi star in the star family, such that Ls pi then can be understood as Ls plus IT pi star. So after a shift, the L functions of pi are the same as the L functions of the pi star guys that are normalized in such a way. So the central character is trivial on the embedded positive numbers. Now more generally, so this story goes through for Rankin-Selberg L functions. If pi and rho have corresponding IT pi and IT rho, then the L function LS pi rho can be understood as the L function of the normalized Rankin-Selberg. So the normalized Rankin-Selberg L function shifted by IT pi plus IT rho. Now here we can see why this normalization is useful. So when you normalize pi and rho, you can, so for the normalized pair, a pole can only occur at the point 1. So for the non-normalized L function, if the L function is not entire, the pole occurs at 1 minus IT pi minus IT rho. So we know exactly where a pole can be, and if it exists, then that is a simple pole. And this pole exists if and only phi star and rho star are duals of each other, contragradients of each other. Now, we have good results for standard L functions. So by standard L function, I mean LS pi. So the usual logarithmic zero-free region for the Riemann zeta function by Delavallee-Poussin has been extended to standard L functions, and Siegel's non-effective zero-free region for quadratic L function has also been extended. So here I collect some of these results. So the first general non-vanishing result for LS pi, standard L function, was established by Jacques Shalaika, and then under some assumptions, fairly general results have been established by Moreno and Hofstein Ramakrishnan. But as far as I know, the first written general account of the standard zero-free region for LS pi follows from a more general result for special Rankin-Selberg L functions by Brumley in 2019, and it reads as follows. So depending on n, there is a constant with the following property. This constant is effective, that for every normalized cuspidal representation of GLN, the corresponding standard L function LS pi has at most 1 0 in this usual looking standard zero-free region. And if the exceptional 0 exists, then necessarily pi is self-dual. So there can be at most 1 0 in that region, and we have a restriction on pi when that happens. And also here is a result that is actually now a special case of the more general result I'm going to talk about today. So this is a generalization of Siegel's theorem for quadratic twists of standard L functions. But anyways, let me not spend time on that because I will show you a more general result. Now, for general Rankin-Selberg L functions, the first non-vanishing result was proved by Shahidi. So the L function doesn't vanish on the one line and to the right of the one line. And then, basically, we only have one general zero-free region for Rankin-Selberg L functions, well, at least up to the current work. And in particular, when you want an effective zero-free region, then basically we only have Brumley's result from 2 papers in 2006 and 2013. So for shift normalized pi and rho, so for a shift normalized Rankin-Selberg L function, we do have a zero-free region, but this zero-free region is very far from being logarithmic. So you see, unlike in the previous case when we took the logarithm of Cp and the imaginary part of S, here we take a large power depending on the degree of the L functions of the conductors and also the imaginary part of the variable. So this is very far from being a standard zero-free region, but it's a much stronger result than Shahidi's non-vanishing result. You can go slightly to the left of 1, and the constant is effective here. Now the exponents n plus m and nm have been improved, but only slightly, say by a factor of 2 or something similar. Now, on the other hand, for special Rankin-Selberg L functions, the standard zero-free region and also Siegel's non-effective quadratic twist estimate lower bound and zero-free region have been extended to special Rankin-Selberg L functions, and so we'll see in a second what special means. On the way, important milestones include results by Moreno, Sarnak, who showed a new way of establishing standard or standardized zero-free regions, and paper by Goldfeld-Lee, who worked out some of the details that Sarnak outlined, and there is also a result by Humphreys under the assumption of the Ramanujan conjecture. At any rate, the result I want to display here is a concatenation of result by Bromley in 2019 and Humphreys-Turner in 2022, and it says the following: there is an effective constant such that for a twist-normalized Rankin-Selberg L function, under the assumption that one of the guys is self-dual or the two guys are dual of each other, so for this restricted family of shift-normalized Rankin-Selberg L functions, we have a standard zero-free region with at most one exception 0 in there, and that exception 0, if it exists, is necessarily simple and real, and that can only occur when either both guys are self-dual or if the two guys, pi and rho, are duals of each other. So once again, this is under restrictive circumstances. Pi is equal to pi tilde, or rho is equal to rho tilde, or rho is equal to pi tilde. So then we have a standard zero-free region with the, at most one exception that we are used to. And of course, if you want the exception 0 to be real, that's where the star normalization, the shift normalization helps. Anyways, here I also display one generalization of Ziegel's theorem for quadratic twists achieved by Humphreys and Turner in 2021, but this is again for a very particular family for quadratic twists. And now the message, if you want to take home some quick message from today's talk, is that Ziegel's method, this non-effective method, works not only for quadratic characters, but it works for all characters, including the Archimedean aspect. So that was not observed before. And interestingly, as you will see, the auxiliary L function is not quite the kind of auxiliary L function that Ziegel used. It more resembles the auxiliary L function that de la Vallée-Poussin used. So there is a nice, so somehow these classical methods of de la Vallée-Poussin and Ziegel come together in this new work of ours. And I want to spend quite a long time on the proof, because the proof is very nice and it is interesting, it's enjoyable. Anyway, so we extended Ziegel's celebrated lower bound for quadratic Dirichlet L functions to all GL1 twists of Rankin-Selberg L functions, and as a result, we substantially improved on Bromley's lower bound in the GL1 aspect, but the price to pay is that the dependence on pi rho is no longer effective. So in Ziegel's result, there is an undetermined and ineffective constant depending on the epsilon there. Here, that ineffective constant will also depend on the initial data, pi rho. In particular, the result that you can read here and we'll review shortly contains Ziegel's result as a special case when pi and rho are the trivial representations and chi is a quadratic twisting character. Then the result that is displayed now here, result from last year we achieved with Jesse, becomes Ziegel's ineffective lower bound. No, no more conditions. But the constant depends on pi, rho, and epsilon, and it depends in an ineffective way. So it's best to think of this result as twisting one Rankin-Selberg L function by all GL1 characters. So if you want to vary pi and rho, then this theorem is not as useful. But as long as pi and rho are fixed, it's a nice result. You can see that we have not only non-vanishing, but in fact a lower bound when we go slightly to the left of 1. Now you might think first, so if you are not familiar with this adelic language that I outlined in the beginning, in the first slide, then you might think this is a non-vanishing result only on the real axis. But in fact, this chi incorporates the t parameter as well. So in particular, when you read this result, mentally you can change chi to chi twisted by the determinant character, determinant to the it. And then the left-hand side becomes L sigma plus IT. So you can squeeze in an IT shift by upgrading chi. And then, of course, in C chi, you have to upgrade chi to chi times the determinant character, determinant the IT character as well. So in particular, if you take chi to be a purely determinant character, chi is determinant, norm of the determinant to the IT, then the result becomes a zero free region for the Rankin-Selberg L function per cell. So L sigma plus IT pi cross rho can be lower bounded by this ineffective constant times t to the minus epsilon, as long as sigma is not too far to the left of 1. Namely, sigma is bigger than 1 minus this ineffective constant times t to the minus epsilon. So it's a rather general result, but it features an ineffective constant. So this is the new result I'd like to discuss today. And as I said earlier, the group structure of F1 is very central to the proof. In particular, this group action of F1 on the larger family Fn. And the proof also utilizes an auxiliary L function that actually generalizes, in a way, the original auxiliary L function considered by de Laval-Poussin, say the product of shifts of zetas or products of shifts of Dirichlet functions that we all know from school, from analytic number theory 101. So we generalize that to this Rankin-Selberg setting. Okay, here are some applications, just very quickly. So once we have a zero free region, or the ineffective, so this Ziegel like zero free region for character twists, then we can also generalize the Ziegel-Waalfisch theorem to the coefficients of the logarithmic derivative of Rankin-Selberg L functions. So the von Mangold function generalizes when you replace the Riemann-Zeta function by the logarithmic derivative or Rankin-Selberg functions. Then you have these generalized von Mangold coefficients, and we can sum up these von Mangold coefficients in arithmetic progressions, m up to x, with moduli going up to log x to the a, any power of log x, just as in the original Ziegel-Waalfisch theorem that doesn't rely on Ziegel's theorem from 1935. And we have a main term and a pretty good, although ineffective, say, error term. So logarithmic saving, arbitrary log power saving in the error term. So we have that. So it follows in a pretty standard way from this zero free region that we have. Another application is that we can now say something about twists of symmetric power L functions with symmetric powers going up to the 8th power. So if you only go up to symmetric fourth power, then by the functoriality results of Kim, Shahidi, and Kim, the estimate I'm displaying here follows from the non-vanishing, the zero free region for standard L functions. Because up to the 4th power, the symmetric power L function is known to factor into standard L functions. But for the 5th, 6th, 7th, and 8th power, such results are not available as of yet. But still, by observing that for these higher symmetric powers and their GL1 twists, we do have some expression in terms of lower rank symmetric powers. So there are the Clebsch-Gordon relations from representation theory, and keeping track of parameters, one can in fact see that these higher up to 8th power twisted symmetric power L functions can be expressed as a ratio of lower rank Rankin-Selberg L functions. So if you look at this expression on the right-hand side, this ratio, when n is at most 8, then all the symmetric powers occurring there have exponent at most 4. So all these symmetric powers by the functoriality results are automorphic on the respective GL groups. So we can use upper and lower bounds for the numerator and denominator achieved by our general theorem and conclude that this twisted symmetric power L function obeys good lower and upper bounds on the one line and to the right of it. So it's interesting that for this upper bound, we need our lower bound because we express the L function as a ratio. So even the convexity bound doesn't come for free, but now it's available due to our lower bound. Anyways, these were just 2 quick applications, and we hope further applications will come on the way. And now I jump into the proof, so I still have 30 minutes, that's good. So I do want to spend 30 minutes on the proof. Now, but the convexity bound for the derivative of the twisted Rankin-Selberg L function, it suffices to simply prove a lower bound at the point s equals 1. So once you know that at the point s equals 1, the L value is largish, you can go slightly to the left of 1 and see that the L value is still largish because the speed of decrement of the L function as you go to the left of 1 is just controlled by the size of the derivative, and the derivative is not too large. So if you can have a seek height to the minus epsilon lower bound for the value at 1, then you have the more general same looking lower bound even slightly to the left of 1. So we focus on sigma equals 1. And this lower bound, interestingly, will be achieved by 3 applications of a key proposition. So there will be an incremental nature of our proof. So as you will see, I will review this key proposition shortly, but as you will see, first we establish this lower bound for determinant characters. So determinant to the IT type of characters. Then in the next step, we'll establish this lower bound for a larger family of characters, those generated by the previous, the determinant characters and quadratic characters. And in the third run, we can get rid of all the assumptions and get this result in general. So it's an incremental proof. We see this often in mathematics when a theorem relies on a special case of it, and we always cherish those situations. This is one of them, and this is an incremental proof in 3 steps. So the key proposition that we shall use, and I will review the proof of it, is the following. So let pi rho chi as before, GL and GLM and GL1 unitary Casimir representations. Let's fix an epsilon between 0 and 1/2. Think of epsilon as being small. And let beta be a real number very close to 1, namely between 1 minus epsilon over 8 and 1. And here is a technical assumption which will be very important for us. Let's assume that these 3 twisted Rankin-Selberg L functions, so the original Rankin-Selberg, the chi-twisted Rankin-Selberg, and the chi-square twisted Rankin-Selberg are all entire. So let's assume we are not in the tricky situation when one of these has a pole. So let's assume none of these has a pole, but nevertheless, the first guy at beta encounters a 0. So beta is a 0 of the first guy. Then so if LS pi rho has a 0 close to 1, then all the twisted versions of it obey at the lower bound we would like to establish. But this only works, this key proposition, the way we prove it only works when not only the chi-twist, but also the chi-square twist is entire. And we have to worry about the cases when they are not entire, because in that case, key proposition doesn't work. Anyway, sometimes the key proposition is not applicable because the middle guy or the right-hand guy, the chi-twist and the chi-square twist, does have a pole. And these situations we handle, these exceptional cases, we can handle with the help of a finiteness lemma that's very well known in representation, automorphic representation theory, namely that up to determinant twists, there are only finitely many characters that produce a pole for the twisted L function. Namely, if you want to prove this finiteness lemma, then without a loss of generality, you can assume that pi and rho are already shift normalized, so that they lie in Fn star and Fm star respectively. And then because we are only looking chi in the star family, so no determinant twist business, then this guy has a pole if and only if pi and the twisted version of rho are duals of each other. But that means that chi, which lies in F1 star, can only ramify where either pi and rho ramify. So the ramification locus of chi is controlled. On the other hand, if you look at the central characters of pi and rho twisted by chi, you can also see that some power of chi is determined. If you fix one chi such that this guy has a pole, then all the other chi's relative to it have a fixed order and restricted ramification locus, and then actually by the compactness of the AQ1 modulo Q star, you can easily see that there are only finitely many characters. So we'll see in a second how this finiteness lemma helps. Anyways, now I'm jumping to proving this lower bound, and as I said, I will do this in 3 steps. In the first step, I will assume that chi star is trivial. So the star part of chi is trivial, meaning that chi is simply a determinant character, determinant to the IT. I denote those characters. In other words, we assume that the chi star part of chi, so the chi star normalized version of chi is trivial. So these characters form a subgroup of all GL1 characters. So let's see how the proof goes for the case of chi star equals 1. Well, that actually corresponds to this special case I mentioned here. So we maybe as a first step, we want to establish this special case only. Well, we can assume that LS pi rho is entire. Why can we assume that LS pi rho is entire? Because if it's not entire, then pi and rho up to a shift are duals of each other. And when pi and rho are duals of each other, I already told you a better zero-free region. So we can assume that we are not in the case when the original Rankin-Selberg has a pole. So we can assume that our Rankin-Selberg is entire. And also we can assume that it has a 0 close to the 1 line, because if it doesn't have a 0 close to the 1 line, then we already have a very good zero-free region. So here we want to establish a zero-free region, so we can assume we don't have a super strong zero-free region. Otherwise, we are done by known results. Now, okay, so we assume now that this guy is entire, and it has a 0 close to the 1 line. So, so in particular, that means that there exists a beta and psi, where psi is actually 1. So this is a strange language I'm using here, which will help us later. So I want to record 1, 0 of the Rankin-Selberg function. I record this as beta, but I want to think of the pair beta and the trivial character as 1 data. So depending on pi rho epsilon, there is this pair psi is not the trivial character. I'm wrong. So we can assume that our Rankin-Selberg function is entire and has a 0 in the half plane, which in particular means that at least one twist in our family has a 0 close to the 1 line, and I kind of fix a smallest 0 and the smallest twist for which that happens. Then this pair beta psi only depends on the initial data pi rho epsilon, and for this particular twist and beta, we have this 0. And now we make a change of variables, so we pass from rho to rho twisted by this psi, which now depends on the initial data, and we twist chi by the inverse of this fixed character, and we think of chi prime being the new variable in terms of rho. So we pass from rho to rho twisted by psi, where psi has been determined as above, and we pass from chi prime to chi twisted by psi inverse, and then we apply the key proposition for the new data for rho prime, chi prime, epsilon prime in the rho of rho, chi, and epsilon. Epsilon prime is just a scaled version of epsilon. So the new notation allows us to say that pi twisted by this new rho, but note that the new rho depends on the old rho, because we get the new rho from the old rho by a twist determinant twist. Yeah, right. So now I realize what this psi is actually. So we have a 0 in this half plane close to the one line, and the imaginary part is encoded in the psi, and the real part is encoded in beta. I want to deal with real zeros. That's why. So wherever the 0 is in the half plane, it has a real part beta. It's like beta plus IT, and then psi is just determinant to the IT. So that's what I work with. Because the key proposition deals with, for convenience, deals with real zeros. But I can encode a real zero. I can encode any zero as a real zero of a determinant twist of the original Rankin-Selberg function. Anyways, so here we shift the Rankin-Selberg function according to the imaginary part of this hypothetical zero, and then that shifted guy has a real zero. And now we observe that the key proposition is applicable because all these three L functions are entire. Let's see why. Because all these L functions are actually just shifts of the original function that was already assumed to be entire. So no funny business with poles here. This middle guy is actually or original twisted Rankin-Selberg function. So if you look at rho prime twisted by chi prime, so rho prime comes from rho by twisting by psi, and chi prime comes from twisting chi by psi bar. So rho prime twisted by chi bar is the same as rho twisted by chi. So this middle L function is just the original twisted Rankin-Selberg function. And the first guy, because of our notation, has a 0 at beta, and all these three L functions are entire because they are just shifts by purely imaginary numbers of each other. So we do get, so if you believe the key proposition, then by the Ziegler-like argument, because you don't have to worry about the pose, you do get the required lower bound. So once again, this is just a special case of our result in the T aspect, because we are only looking at this point at step one. In step one, we only look at GL1 characters whose chi star is 1. Anyways, once you know that for every element of this subgroup, we have a good lower bound. So we do have the lower bound. So we do have the lower bound for chi lying in this subgroup, F11, defined by chi star equals 1. As a formal consequence, for any fixed coset of F11, the result also follows. So by fixed coset, I mean you choose any known element of F1. So you specify any element of F1, and then if you think of chi lying in a coset of F11 shifted by this fixed element of F1, then you can think of the corresponding twisted Rankin-Selberg function. So if chi lies in a coset of F11, you can think of the twisted L function as twisting by an element of F11 a slightly different L function, namely, so chi is of the form something like chi 0 times an element of F11. So you upgrade rho to rho twisted by chi 0. So you change the data pi rho, but it's still, you can think of it as fixed data because you think about a fixed coset. And so you get for free, just by this little group theoretic idea, this non-vanishing result, not just for the subgroup, but for any fixed coset of it. So that's important. So in the first step, I established the non-vanishing result for this simple-minded subgroup of GL1 characters. And then as a formal consequence, we have it for any fixed, it happens in every fixed coset of it as well. So not just a subgroup, but any translate of it, any fixed translate of it also works, just by formal reasons. Now, in the next step, I look at the case when chi star is not necessarily trivial, but it's quadratic. So that is to say, chi is a quadratic character multiplied by determinant character. In the first step, we looked at determinant characters. Now we look at all the quadratic characters multiplied by determinant characters. So these characters form a bigger subgroup. I call it F12. And now again, we can assume that LS pi, so the twisted L function is entire, because if it's not entire, then by the finiteness lemma, chi lies in finitely many cosets depending only on pi and rho of the previous subgroup. So remember, in the finiteness lemma, we determined there are only finitely many choices for an element of F1 star so that the twisted L function has a pole. So if in this step 2 we encounter a pole for LS pi twisted by rho twisted by chi, then chi is constrained to finitely many cosets of the previous subgroup defined by chi star equals 1. Because writing down chi star, having finitely many choices for chi star is the same as chi lying in finitely many cosets of the subgroup defined by chi star equals 1. It's just simple group theory. So by this last remark, this formal remark, step 1 allows us to assume at this step 2 that the twisted Rankin-Selberg L function we are dealing with is itself entire. And then again, this entire twisted Rankin-Selberg can be assumed to have a 0 in this half plane. Otherwise, we have a much better zero-free region. So what's happening here? Our twisted L function is assumed to have a 0 in this half plane, which means that definitely there is a twisting character depending on the initial data only, which has a 0 on the real axis close to 1. So it's very tricky. So if you know that for one twist, there is a 0 close to the 1 line, that means there is also a GL1 twist with a 0 on the real axis close to 1. And then among all these GL1 twists, you can choose the smallest one. And at that time, the data I fixed here, beta and psi, such that LS pi twisted by rho twisted by psi is entire and vanishes at beta, now a real number close to 1, only depends on the initial data. And then we start measuring chi relative to this psi. So we make a change of notation, just as in the previous step. So we twist rho by psi, and we untwist chi. So we twist rho by psi to get a rho prime, and we untwist chi by psi bar to get a chi prime. So note that in this new notation, rho prime twisted by chi prime is the same as the original rho twisted by chi, and we apply the key proposition just as before for this updated data. And the way so by our setup, the first guy, LS pi twisted by rho prime for this upgraded rho, has a real 0 beta. So this beta comes from the assumed exceptional 0 of some GL1 twist. So we assume some GL1 twist has a 0 close to 1 line. So that means some other GL1 twist has a beta 0 close to 1. And our LS pi twisted by rho prime now has a real 0 beta close to 1. And I claim that the key proposition is applicable because the other two guys, the chi prime twist and the chi prime square twist, are also entire. Well, the middle guy is entire because the middle guy is the same as the original twisted Rankin-Selberg L function that was assumed to be entire. And how about the third guy? Well, if you look at the third guy is the chi prime square twisted version of the first one. But chi prime here lies in our family that satisfies the star version square equals 1. So this chi prime squared is actually a determinant character. So the third L function here is just a shift of the first L function. So it's really amazing. In this step 2, you get the holomorphicity of the third guy for free just by the very setup. And this way we did upgrade our result from the first subgroup of twisting characters to this new subgroup of twisting characters that now includes all the quadratic guys. So it's a bigger subgroup. And as before, just for formal reasons, once you have the non-vanishing result in the lower bound for a subgroup, you also have it for any fixed coset of it. So the same kind of formal game with group theory. So here in the first step, we had a result for F11, and then we also have for free in any coset. And now we established it in F12, bigger subgroup, and just for formal reasons, in any fixed coset of F12, we also have the non-vanishing result and the lower bound. And now comes step 3, the general case. So now we look at an arbitrary GL1 twisting character, and as before, we can assume that this guy is entire by the finiteness lemma, and then just as before, so this is the same thing as before, we can record, say, this smallest GL1 twist for which the twisted Rankin-Selberg function has a real zero close to 1. So depending on pi and rho, we again fix beta, which is actually the real part of say the smallest twist with a zero close to the 1 line, and the psi part as well we fix. Anyways, but the advantage now is because we have already established the case of chi-star being quadratic, we can now also assume that the chi-prime square twist, so we change notation as before, so we upgrade rho by twisting it by psi, and we upgrade chi by untwisting it by psi, so it's just change of variable with this new data, psi bar that only depends on the initial data. And now we can assume that the chi-prime square twisted version of the Rankin-Selberg of the new data is entire. Otherwise, we are done by the finiteness lemma step 2. So now, why? Because if this is not entire, then chi-prime squared has the feature that its stored version comes from a finite family. So there are only finitely many cosets of the previous subgroup of characters for which this chi-prime square twist is not entire. So if it's not entire, then we are back to the previous case. It's very tricky, very interesting. And so because we had step 2 and we have the finiteness lemma, we get for free the assumption, we can assume without loss of generality, that this chi-prime squared twisted guy is entire. And now we apply the key proposition just as before with this upgraded data, rho prime, chi prime, epsilon prime. Once again, epsilon prime is just this scaled version of epsilon, it's nothing serious. And we can apply the key proposition because now by all the assumptions, all the 3 L functions are entire. The middle guy is entire because it's just the original twist. This first guy is entire because that's just the L function in this assumption. And the third guy is entire because we just discussed that we can assume that it is entire. So this is how we prove the lower bound, this lower bound in 3 steps. Of course, the key proposition made it happen. 3 applications of the key proposition in various instances of the key proposition. And for the key proposition, we'll need an auxiliary L function. And so that's maybe the most analytic part of the result. So first of all, here is just a little remark. If pi is twisted to itself by chi-star or rho is twisted to itself by chi-star, then we can assume that the t parameter of chi is not close to 1, because if the t parameter is close to 1, then the twisted L function in this situation is just, the value is just varying in the variable is varying in a compact set, and we have non-vanishing, so we have a lower bound by just Shahidi's result. So it's just a technical assumption that in the case when pi enjoys a self-twist by chi-star or rho enjoys a self-twist by chi-star, then the t part of our twisting character is not close to 0. It's just a technical assumption. Anyways, here's the real deal. So now we introduce our auxiliary L function. So we have the initial data, pi and rho, and we are interested in the quite twisted Rankin-Selberg L function. So we form this isobaric sum, pi plus pi twisted by chi, then the dual of rho, and the chi bar twisted version of the dual of rho. And then from that, we form a self-dual Rankin-Selberg L function. This auxiliary L function, being of the shape Ls capital pi cross capital pi tilde, has non-negative Dirichlet coefficients by a general result of Hofstein-Ramakrishnan. So self-dual L functions have non-negative Dirichlet coefficients. That's convenient. And if you keep track of, so there are 4 summands in this isobaric sum, so there will be 16 L functions after the pairing. So there are 2 plus 2 plus, so there are 8 in the first row, 4 in the second row, 4 in the third row. So it looks a somewhat scary expression, but this product of L functions just is the key to the proof of the key proposition. Okay, so the conditions ensure, what are the conditions? So in the key proposition, we are assuming that none of those 3 L functions, so pi cross rho twisted by chi and pi cross rho twisted by chi square. So none of these twisted Rankin-Selberg L functions have a pole. So if you look at these 16 L functions, in the first row, only the first two factors can have a pole because the other two factors include pi and rho and one of the twists by chi or chi bar. And in the second row also, only the first two guys can have a pole because the other two guys are the ones that we excluded to have a pole. And the third line also, only the first two guys can have a pole because the other two, here we have pi cross rho, here we have pi tilde cross rho tilde by chi bar square. So all the hybrid Rankin-Selberg L functions in this product and their twisted versions are entire by assumption in the key proposition. So you only have to worry about poles in the first two factors in either of the three rows, and those guys include pi and its dual or rho its dual. There is no mixture with pi and rho, only pi tilde or rho tilde. And so if you look at the first line, that tells you that, so these first two factors can only have a pole at s equals 1. In the second case, the pole can only be at 1 minus it chi, and in the third row, the pole can only be at 1 plus it chi. So we have a very good idea where the poles can be. There can be at most 3 poles, either 1 or 1 minus it chi or 1 plus it chi. Now the pole at 1 always occurs, and it has order 4. With multiplicity, there are 4 poles coming from the first line. But from the second line, which might contribute the pole 1 minus it chi, or this third line, which might contribute the pole 1 plus it chi, those poles might not be there. The pole can only be there in the second line when pi is the dual of pi twisted by chi, which happens if and only if this pi enjoys a self-twist by chi star. And from the second line, we get a pole likewise. So these two cases that I sorted out in the beginning as a technical assumption here, they actually are about the case when there is a pole coming from the second line and the pole coming from the third line as 1 minus it chi and 1 plus it chi. Anyways, so we have ds, but our original twisted Rankin-Selberg is sitting in this product, so this auxiliary L function does vanish at beta. Beta is our exceptional 0, close to 1. Hence, even when you multiply this ds by the appropriate gamma shift, it will have no pole other than the ones already listed in the positive half plane. Anyways, now a standard application of the residue theorem, having in mind that our auxiliary function has non-negative coefficients, actually yields this upper bound. Here, the second integral can be estimated by the convexity bound for ds. So the convexity bound for ds comes for all the convexity bounds. So convexity bounds for all these factors. And here it comes handy. Here it is important, actually, that t chi is bounded away from 1. So if the poles are too close to each other, then we have trouble in upper bounding ds. So that technical assumption was about that. Anyways, this is controlled by the analytic conductor of our Rankin-Selberg and the analytic conductor of chi. And so, in effect, we get a lower bound for the sum of residues. So here I repeat what I already said, that the pole 1 always has rank order 4, whereas the pole 1 plus minus it chi, if it is there, has order 1 or 2, depending how many of these self-twists are happening. If none of the self-twists are happening, then these poles 1 plus minus it chi are not there. If one of these self-twist equations is true, then the order is 1. If 2 are true, then the order is 2. And now and of course, then we can calculate the residue. Once you know the order, the residue is just 1 over k minus 1 factorial plus k minus 1 derivative of this product. It's just standard, Laurent series complex analysis business. Anyways, we need to take the k minus 1 derivative of this expression. Well, the first factor and the third and fourth factor are just innocent. You have to worry about the k minus 1 derivative of ds. But here comes the punchline. It turns out that in each of the cases, for the pole 1, or for the pole 1 plus it chi, or for the pole 1 minus it chi, regardless of the value of chi being 4 or 1 or 2, the product ds always has at least k factors whose size, k factors meaning k of these 16 factors. There are always as many factors as the order of the pole L function factors whose size at the point as 0, which is the pole, 1 or 1 plus minus IT chi, has size being the size of our twisted Rankin-Selberg L function. So if you differentiate ds k times a la the Leibniz rule, actually k minus 1 times a la Leibniz rule, because there are k factors whose size is that one. One of these k factors survives the differentiation process. So this residue can always be upper bounded in terms of the twisted L value at 1. And then a standard argument just gives what we wanted to prove, the lower bound in terms of the analytic conductor raised to the minus epsilon of our L value. And I have 4 seconds left, and this is my last slide. Let's just have a final look at the auxiliary L function. In the special case, pi and rho, if you keep track of it, it just specializes to this very familiar product of Dirichlet L functions. So really, we have generalized de Levallois-Poussin's ideas and Ziegel's ideas simultaneously to this zero-free region for twisted Rankin-Selberg L functions. Thank you.
Well, thank you, Gergely, and yeah, well, good job sticking to the time. Are there questions?
Yes.
Yes, Jakob.
Maybe you want the microphone.
This is where, oh, well, I guess it's hinted at by the last sentence, but the obstacle in getting a standard zero-free region is somehow not having control on the logarithmic derivatives, I guess.
No, the ineffectivity comes from all these data that we. So the idea of Ziegel is you are looking at a family of L functions and you want to show a zero-free region for all of them, and assuming one of these L functions in the family has a 0 close to the 1 line, then in terms of this exceptional 0, you can get a better lower bound for the other members of the family as otherwise would be possible. So that is actually hidden in, whenever we say in particular there exists beta, beta is this real part of the 0, and psi, which is kind of the smallest twist where the exceptional 0 is happening, actually just the star part of the smallest twist. So we fix this beta psi, that's in terms of pi rho, that's in terms of pi rho, and also here we use Shahidi's result, there is also some undetermined dependence on pi rho. So that's where the ineffectivity comes from. We don't know where the exception, well, we hope there is no exceptional 0, but if there is one, we have no idea where it is. Yeah.
Thank you. More questions? Okay.
Hi, Georgia.
Hi, thank you for the wonderful talk. I just wanted to ask, at the end you said that you're going to get at least k factors that are of certain size.
Yes.
But are they somehow magically of that size, or are they literally that?
It just happens.
Because
it's a bit magical. It's a bit magical. I can show you how it happens. Let's just look at s equals 1, and that has order 4. Just look at it, and then you see the magic. So in the first line, there is an order 4 for s equals 1 coming from these 2 factors. But if you plug in s equals 1 to these 2 factors, you get the twisted guy and the dual of the twisted guy. So you get 4 copies of 4 L functions with the same size being the twisted guy. So when you look at the pole s equals 1, whose order is 4, you do get next to it 4 factors whose value at s equals 1, after you put the absolute value, is of the same size as the L function you want to look at. But then there are also the other kinds of poles, like 1 plus it chi and 1 minus it chi. So we get 1 minus it chi in the case when chi star twists pi to itself. That's the only case. That's the only way it can happen, that there is a pole at 1 minus it chi here. But if chi star twists pi to itself, then if you plug in 1 minus it chi here, then this is actually in absolute value that has the same size as our twisted L function, because the chi. So plugging in s equals 1 minus it chi is the same as twisting pi tilde by chi bar, but pi tilde twisted by chi bar, yeah, so L 1 minus it chi pi tilde cross rho tilde under the assumption that pi twisted by chi stories pi is exactly the same as L1 of pi tilde twisted by rho tilde twisted by chi bar. So if you get a pole in the first factor, then this third factor does the job. If you get a pole from the second factor, then actually the fourth factor just does the job. Because if the second factor has a pole at 1 minus it chi, then this second self-twisting relation happens. And when you plug in 1 minus it chi here, because this chi star is now special, twisting by chi star is the same as shifting the variable by 2 it chi, but as was 1 minus it chi, if you shift 1 minus it chi by 2 it chi coming from the chi star, you do get L1 plus it chi pi twisted by rho, which is the same as L1 at pi twisted by rho twisted by chi, again by this relationship. So it just magically happens that there is always a matching number of good other L values whose size is the same as what you want to estimate. So I don't have a very good explanation why this is happening. I just see it, it's happening. Yeah. And actually, what's interesting, yeah, we cooked it up. Our original construction didn't have 16 factors, but 36 factors. And I kept saying, no, it's too complicated, it can be simplified. And then we were down to 16. In fact, for a while we believed, no, it doesn't work, then it doesn't work. And then after all, we calmed down, yes, it really works. It was only in retrospect that we realized that it actually generalizes the de Laval-Poussin. So it was not like we took the de Laval-Poussin proof and we tried to cook up this auxiliary function. No, it was the other way. But now it seems very natural. I think this is kind of minimal for the proof. Sorry? Yeah, sure. It must have degree 16. It's the same thing.
Yes.
6 plus 4 plus 4 plus, yeah, that's 16. That's good. Well, the way we learn the proof, we are used to third power, second. Well, everything is doubled here. So if you take the logarithmic derivative of that, then that's the same as the real part of the logarithmic derivative with half the coefficient, zeta s to the 3 ls chi squared and ls chi squared bar. We usually look at that product, we take the logarithmic derivative, and then we take the real part. But taking the real part is the same as matching up with the dual guy. So in the end, you are really talking about the logarithmic derivative of this guy, which is of degree 16, not 8. That's good. Yeah.
Very much. And well, let's thank our speaker again.
Thank you.